So at the end of class on Monday, I asked you to help me figure out how many steps we finish here. What happens as I continue examining possibilities for J in all of these additional layers? Blake?
The I equals 3 would be 4 and then 5 on n, so it would be n minus 3 times.
Right. So by the time I get down to here, if I'm at n minus 2,
Be n plus 1, then n, then 3. Yeah. Well,
it's got to end at n. But where's it going to start?
n minus 2. Then n minus 1.
If this starts at n minus 2, that's the same as this.
Oh, yeah, plus.
Aha. And that means here I have 2 steps, and here I have 1 step. And here I don't have any. Because J goes from I plus 1 to n. I'm going to go from n to n. I'm going to go from n plus 1 to n. That doesn't happen. So I have to drop out. So this is the total number of steps I have right here. So now my question is, what does that add up to? Now, before you lose your go, I don't know how to add that up. I'm going to rewrite it. The number of steps in that box is that much.
I've seen this before.
What's that total? Colin? Remember, we did the pairing up when we added up from whatever. Each pair is going to be n. So I have n pairs, n for each pair, and I have n minus 1 over 2 pairs. Right? There are n minus 1 numbers here. So half of that is the number of pairs, and each pair is n. That's the same as 1/2 n squared minus 1/2 n. Which makes this big O of n squared. This algorithm is big O of n squared. No matter how many pairs of numbers I need to multiply. You give me a list with 100 numbers, it's on the order of tens of thousands of steps. You gave me a 10 to the second, it's going to take me 10 to the fourth steps. Roughly. Because I did 2 steps this many times, multiply this by 2, big O of n squared. Questions? Depending on the way the algorithm is written, I may or may not find it obvious to determine. If I go back and I look at the code for this, I say to myself, that first counter, it's got to go from 1 to n. And each time I do that, I'm going to run another counter that's going to go to n. It's not always going to start in the same place, but it's going to go to n. If I got an n inside an n, isn't that n squared? So here's a general heuristic. I can actually say, if I don't want to be super precise, that all I have to do is count my loops, provided I know how big each loop is getting. Questions? Here's another algorithm we already quote know. Binary search. Here's my search algorithm. If I want to count the number of operations involved here, and my list has n numbers in it, sorted in order already, from smallest to largest. I don't care how many it is. How many times am I going to go through this loop? Because there's only one loop involved here. This while loop. I do 1, 2, 3 steps in this line. I add, divide by 2, and I round down. I do a comparison, and then one of 2 other additions. So in this loop, I'm doing 5 operations. If you can tell me how many times we're going to go through the loop, then it'll be 5, whatever that is, number of steps, right? When we're done with the loop, we do a comparison and then spit out one of 2 things. So there are 2 more steps when we're all done with the looping part. So now I need to figure out how many times I'm going to do this loop. This is where I need to think heuristically about what this algorithm does. We went through this algorithm explicitly. How did we decide what to do when we did this? Started with that list. I think I was looking for 19, 17, something like that in my example. I took the list and I looked in the middle. And I said, okay, this number, one less than the middle, is that my number? And if not, is it bigger or smaller than my number, right? Is it bigger than? If it is, move this side to here. If it isn't, move this side to here. And I cut the list in half. And then I did that again, right? That's what the binary part of this binary search is. I keep cutting the list in half. So let's suppose I start with n items. I go through the list, the loop once. How big is my new list? N over 2. Second time through the list. I'll divide it in half again, won't I? Third time. Thrice through the list. And so on, right? But every time I divide it, I'm looking at I and j. Eventually, I end up with one and only one number. And when I have one and only one number, then I and j are equal. And I stop going through the list. So eventually, this number is going to be 1, or it's going to be a fraction of something bigger than 1, right? Like 1.5, because we keep rounding down. We do floors in here. At some point, I'm going to have 1. I don't know how many steps it's going to take. I want to know how many times it took to get here. Let's work backwards. If I started with one item, then the next to the last time I would have had at least two, right? The time before that, 4. The time before that, 8, 16, 32. To get back up to here, to get to the original number of items in my list, I need to keep multiplying by 2. So I want to know when that occurs. How many times did I have to double my size to get at least as big as n? Actually, I should use bigger than or equal to. How do I solve for the question mark in that expression? 11? Log base something. What's the something? That's the base, because that's base power answer. So really, question mark is the log base 2 of n. But I want it to be bigger than or equal to, right? It might not be an actual whole number of steps, right? Grab your calculators. Now I'm going to need you to answer me a question as to how I do this on the calculator. Suppose I have 50 items in my list. How do I get the log base 2 of 50? There are at least 2 different ways to do this on your calculator. One of those requires you to know a formula.
When you say like, how do we get it on that time number?
How do I get this number? Log base 2 of 50.
The math button. Base.
That's the one that doesn't require me to know a formula. There's a log base button. Log base 2 of 50. But that's not a whole number, right? So is it going to take me 5 steps or 6 steps to do 50? Well, think about it. I go from 50 to 25. I can't do 12 and a half, so I'd end up at 12. Then I'd end up at 6. Then I'd end up at 3. Then I'd end up at 1, right? That's 6. I have to round this number up. The other way to do it is to do the log of 50 and divide by the log of 2. That's the change of base formula that I learned in algebra class, God knows how many years ago. But here's the best part. If I round this up, it's just one number bigger at most, right? So it's really the log plus 1. Big deal. But remember, when I'm thinking about complexity, all of the logarithms are equivalent. It doesn't matter whether I'm working in log base 2 or log base 10 or ln. It doesn't matter. This is big O of log of n. In computer science, the default assumption is that your logarithm is log base 2. But one of the comments we made on Monday was that it doesn't matter what the base of the logarithm is. They're all equivalent. And that makes a big difference. How fast was the linear search? That was what we talked about on Monday. The linear search. The worst case was I had to go through the entire list, right? And I didn't find that means the worst case is n. The worst case here is log n. That's substantially faster. That's a whole order of magnitude faster. So if I gave you, I don't know, a gigabyte of data, a gigabyte of numbers, and said, find 3,872, in a linear search, it would take you to search the entire billion numbers. The log of a billion is 9. The log base 2 of a billion is less than 30. Would you rather take a billion steps or 30? That's a hell of a faster move. The problem is that I need to sort my list first to do the binary search, right? And sorting algorithms themselves take time. If I give you an unsorted list, you've got to sort it first. Both the insertion sort and the bubble sort are big O of n squared. And that makes it a problem, because if that part is big O of n squared, I can't make an algorithm faster by doing more in front of it. If I want a faster search, I need a different algorithmic paradigm. I need to think about searching or sorting in a different way. There are faster sorts. Things like the heap sort or the merge sort. What's the third one called? The quick sort. Those are all big O of n log n, which makes them a little faster, but not hugely faster. There are a large number of algorithms we use to do all sorts of computations that would otherwise be really, really, really difficult to do manually. We did root finding. In Calc 1, we did Newton's method. Newton's method is big O of n squared, where n is the number of decimal places I need. The only reason it's n squared is because I have to do a division, f of x over f prime of x. And dividing is a big O of n squared, like multiplying is big O of n squared. That's not non-trivial. But with our levels of complexity, the faster I can make my algorithm, the happier I am. There's an example in the textbook. Example 10. I ate it. Where's my example 10? Here's my example 10. Find the closest pair of points in a set of n points. So I have a bunch of points. Tell me which pair of points. Well, you don't even have to tell me which two it is. What is the smallest distance between any of these 2 points? Now, your first reaction may be, why on God's green earth do I give a flying about this? And let me give you what I consider to be my best answer. If I can tell you how far apart 2 items are in this setup, then I can generalize this idea. Instead of looking at individual pair of numbers, I could look at a whole collection of numbers. Let's say instead of just being X and Y, it's, I don't know, 100 in a row, right? So each of these, instead of being a pair, is a list of 100. Measuring the distance between those is going to use the same formula as measuring the distance between these two. How do you measure the distance between 2 points? X1, Y1 and X2, Y2.
X2 minus X1. Minus Y1.
What do I do with those? Blake?
You put the Y's above the X in a fraction.
That would give me slope. Same idea though, Colin. Except I need to do something before I add these two together. I have to square them, and then I take the square root. That's the distance formula, right? It's the Pythagoras, change in X, change in Y, give me the hypotenuse, right? By the way, taking the square root is not really necessary. If I know which two have the biggest distance squared, sorry, smallest distance squared, taking the square root is still going to keep it smallest. But if I have 100 numbers instead of 2, I would just have x2 minus x1, y2 minus y1, z2 minus z1, a2 minus a1. I could do as many as I wanted, right? I just have to subtract them. Square them, add them together. This same formula can have as many dimensions as you want. Okay, what's my list of numbers represent? My list of numbers represents the details of your face on an oval. Where are the tops of your cheekbones, the centers of your pupils, the centers of your nostrils, the tip of your nose, the dip of your chin, the line that you make where your chin intersects your lip muscle? If I can track where's the tip of your ear visible, the bottom of your ear, the top of your ear, that's a face. Which two are closest? That's a facial recognition software. Here, which face that I saw is closest to this one? I walk down the street in view of Ring cameras, in view of ATM cameras, in view of the dash cam on somebody's car. If those are recorded and stored somewhere, my face is there. You go driving in Pittsburgh and they put in red light cameras, they can see through your car window to your face. Facial recognition is everywhere. Which face is closest to this one? Is this problem? This sounds much more innocuous, doesn't it? So how long is this going to take? If I have n points, if I have n faces, how long is it going to take me to find you? This depends on how I do this problem. Remember, I talked about algorithmic paradigms, the way to figure out how to do my algorithm. There are a lot of different options. I'm going to go with what I consider to be the most direct version of an algorithm. Brute force. Let's try them all and see which one is smallest. Doesn't that make sense? Just try them all. This is like trying to break your password in your phone by typing A, that didn't work. A, that didn't work. If you've still got a phone code, is it 4 digits? There are only 10,000 options. I could do it eventually. What stops me from it?
You get it wrong too many times, it locks it up.
For how long? That depends on how many times I've tried, right? And each time I try, the longer it grows. So they put some protections in place. But the idea is still the same. If I want to go to an ATM and I want to break a password the same way, ATM codes are 4 digits. I put it in, I type 1, I pull it out. I put it in, I type 1, I pull it out. If I do it fast enough, go watch the Terminator 2 movie. I'm about to tell you a little silly secret. In Terminator 2, Edward Furlong, the actor who plays the little kid, John Connor, breaks into an ATM by doing a brute force attack. He just pushes his way through all the passwords. A brute force method would work in this case. So let's think about it. I'm going to start with x1, y1. And I'm going to compare it to all the other points. Yes? So I need to compare it to x2, y2, then to x3, y3, all the way up to xn, yn. And I'm going to do this calculation, which is 2 subtractions, 2 squares, and an addition. That's 5 operations. If I include the square root, it's 6. I'm going to do it this many times. Then I go to the next point. I go to x2, y2. What do I need to compare that with? Colin? Why don't I have to compare it to x1, y1? Because I already did right there. So I can start here with x3, y3 until I get to xn, yn. Wait a minute. When I do x3, y3, I compare it with and everything up, right?
Gee, this looks awfully familiar, doesn't it?
I start with 1, I go from 2 to the rest. I start with 2, I go from 3 to the rest. I start with 3, I go from 4 to the rest. This is the exact same thing, isn't it? Which means I don't need to go any further. How complex is this? It's the same complexity as that multiplication process. There are going to be big O of n squared steps here. N minus 1 times n over 2 times 6. That's big O of n squared. I'm going to sneeze. That's just in the background. I apologize. So with this idea in mind, I don't actually have to have a detailed exact calculation to know exactly, precisely how many steps are required. I have to have this heuristic idea. Can I estimate? And if I can lower that estimate, the lower I can make it accurately, the better I am. Questions? Yes.
Like when these run the test, will it say on the test estimate this?
Or it'll say determine the big O in some fashion. And I better give you code, because that makes more sense to go through and count in code, which is why I like that initial problem. If I keep looking at the algorithm, what do I have here? But when I start with a paradigm, when I start with this is how I'm going to do this problem, then I can get a better idea of what I should be looking for. There are improvements to this process. I could, instead of doing brute force, I could say, pick one point, test everything. Discard the points that were above some number. Pick another point in the set that was close. Problem, if I pick a bad starting point, I'm in trouble. So this is a brute force idea, but now I've got one that says, okay, well, what if I started here? Then it's going to be choice dependent, and analyzing that gets harder. So choosing the way in which you approach your problem, your paradigm for solving it, is an important piece of figuring out how complex the method you chose is. So if I give you the method, then we can analyze it. More questions? In general, we tend to talk about complexity in ranked order. Just like when I was talking about which functions were more complex than others, I can think of what's the big O, or in this case, big theta, they've used the correct notation for a change, of my problem. By the way, the closest pair of points problem, there's my algorithm. Loop 1, loop 2. That's n squared, isn't it? One loop inside another. Something that is constant complexity. Is this number even or odd? I don't care how many digits the number is. If you want to tell me if it's even or odd, what do you have to look at? The last digit. Do I care about how many digits it is? No, just look at the last one. Logarithms, powers. Notice that combo behavior, n times log n. I could then have n squared log n, and n cubed, and n log. Any logarithm is going to bump you up just a little once. It is also possible to do things that are like log of log, which decreases again. I'm not even going to go there. There are many more categories than this. But everything up to this is at worst a polynomial, right? Whether it was n to the third or n to the fourth or n to the 17th, it's n to somehow. As soon as I cross this line from polynomial to exponential or factorial, I've created a function that is not a polynomial. That's the dividing line for complexity, right there. We say that any problem whose algorithm is up here is a tractable problem. That list is on page 242. Any problem in this group is said to have polynomial time complexity. It is at worst solvable in a polynomial based on the number of steps involved, based on the size of the input. These problems are called tractable. So any algorithm that is trying to solve a tractable problem is going to have some complexity up here in time. Down here, we have the non-polynomial time problems. These are called intractable problems. The difficulty is, if a problem is intractable, writing a general solution is impossible. There may be some really nice special cases you can do, but writing the solution and making it solvable in a reasonable amount of time is just not going to happen. My favorite intractable problem is called the traveling salesman problem. I am a salesman. I need to go from town to town with my truck full of stuff and go from store to store to store to store and try and sell my stuff. Right? I need you to find me the shortest trip to the 10 cities I need to visit. I could also ask you for the cheapest trip. If I know the cost of each mile of road that I have to drive, the amount of gas, the amount of wear on my car, whatever tolls, etc., I could put a cost on every piece of road. And I could ask you, what's the cheapest trip? It turns out that the two best known versions to solve this problem are big O of n factorial. Because what you really need to do is you need to write out all the possible lists. So there are 10 first cities, 9 second cities, 8, 7, 6, 5. There are 10 factorial different trips I could take. What is 10 factorial? You have a calculator, you can do 10 factorial. Huh? 3.6 million. So in order for you to find the cheapest trip, you have to write out all 3.6 million of them, price them out, and then sort that list from smallest to largest. Or just do a search for the smallest, right? We can do a search. You don't have to sort. We can just do a search. Now, I don't mean to sound stupid, but this only requires me to go to 10 places. I'm going to drive for Amazon. How many deliveries do I make today? Fill the van and find me the fastest route to all 180 drop-offs I need to make. 180 factorial will break your calculator. Get on the internet. What's 180 factorial? Evan, you were laughing. What's the exponent? 10 to the what? 10 to the 328th. People, the life of the universe so far is 10 to the 40th seconds. Ten to the 328th. I can't even write that list if I could write one list a second. Since the Big Bang, since God said, let there be, and there was, I wouldn't be anywhere near 1% done yet. And that's only 180. Now imagine you're trying to route lots of things. There are special cases. I can say, I'm going to start here. I'm going to end. There are ways to bring this down a little. It's still ridiculously complex. Let me give you a problem you have to do. Here's a propositional function. Is it a tautology? How do you know whether it's a tautology or not? This was on exam 1.
True.
So I have to make the truth table, right? If there are n propositions, that's 2 to the n rows, isn't it? So truth tables, technically, are non-polynomial problems because they're exponential. Now, at the moment, what people are starting to do is they're looking at the algorithms for problems that are intractable. And they're saying, if we make this simplifying assumption, does it become tractable? If we make this little change, does it simplify the problem enough to jump this line? And the other way, true, they're looking at tractable problems and they're saying, can we extend this algorithm just a little to try and take on problems that are up here? Right now, there are problems that we can solve. And there are problems that we have algorithms for that won't complete before the sun goes dark. But mathematically, we think these two sets of problems, the polynomial problems and the non-polynomial problems, are completely separate from each other. If there's any problem that crosses the line, then there'll be a way to merge those problems together. Factoring large numbers is currently in this category. Factoring large numbers is the secret to SSL security on the internet. If we can cross this line, what happens to every cryptography piece we've ever done? The entire future of computability. Is this problem computable? Is answering, where does this line really get drawn? So right now, the Clay Math Institute, back in 2000, created a bunch of problems they said would drive the future of research in computing and mathematics. There is a $7 million bank, $1 million for each problem. That one right there is exactly this question. Is there a way to find the optimal solution to an intractable problem in a tractable amount of time? If you can find it, it's worth $1 million. That Hamiltonian path idea, instead of giving you a list of cities you have to visit each one, find me the cheapest route. Here's an entire map. I want to visit every city once and only once. Starting here and ending here, make me a loop. Can you do it? Maybe. If you give me a list, I can check whether or not it does it. But finding that list in any fashion other than brute force is currently not known to be possible. That's the Hamiltonian path problem. If you're interested in that sort of idea, I would recommend you take graph theory next semester. The prereq is this course. There is lots more I can do in complexity theory. Not just tractability and complexity, but I can actually now talk about speed. Here you go. Let's consider top of page 245. Here's the size of my input data set. If my input data set is 10 things, log of 10, log base 2 of 10, is 3 and change. So it'll take 3 operations. 3 operations at a nanosecond each, right? 1 billion operations a second is a really, really small amount of time. But if my 10 operations is instead big O of n squared, that's still a tiny amount of time. But if it's n factorial, it's now microseconds. instead of nanoseconds. If I go from log n to n squared, we went from 10 to the negative 11th, sorry, to 2 to the n, to 10 to the 8, negative 8th. So I went from 3 trillionths of a second to 1 billionth of a second. Doesn't seem like a huge jump, does it? If I move from 10 items to 100 items, this is now 7 trillionths of a second. This is now 4 billion years. Sorry, 400 billion years. Just from going from 10 items to 100 items. That's how huge these are. These stars right here, these stars are more than 10 to the 100th years of processing power. At today's computer speed, 1,000 items. If I gave you 1,000 cities or 1,000 variables in a proposition and said, solve it, the sun would go dark first. Holy crap. Now, the thing that I want you to take away from this is that even when you can design a solution, can you implement it? Becomes the next question. Is the process doable in any reasonable fashion? One of the most amazing ideas in modern AI is that I have all this computing processing power. I should be able to do everything. No, absolutely not. I can approximate a good answer, but I can't actually get the best answer. So now we go to the next step of that, which is, okay, so what do I have to do to the algorithm itself? What do I have to do to change the design to write a better algorithm? That is the theory of computer science, which this class is not. So I will save that for Dr. Al-Shalwi and Dr. Kisau and whoever else we hire over in that department. And if you really want to do more in-depth behavior on this algorithms analysis, that's the course you should be taking, CS 341, Algorithms Analysis. The majority of that course is trying to figure out how to make the improvements we're talking about, to go from big O of n squared to something smaller. So this is the end of chapter 3. Chapters 2 and 3 make up the next exam, which is a week from today. Because Monday you hand in the homework for 3.2, Wednesday you hand in the homework for 3.3, the review sheet is up, and we'll see you all on Monday.